All right, another physics teachers are awesome reaction video. Today, energy pie charts to set up and solve some physics problems. All right, let's get started.
Let's get at it here. So, I want to set up the 6 problems that are on your celebration that's graded. Talk about that setup a bit more, but leave the work to you. And time permitting, we'll also I'll do some other problems that are like these, typically harder than these, but involving many of the same steps. So
cool. So some scaffolding.
Want to
helping students set things up. Cool.
Let me get my colors set up here. So let's take a few things here. So the first 5 meters.
Oh, cool. That's pretty cool.
Journey is a spring. So we're imagining on this aircraft carrier problem, there's a huge spring launcher to launch these airplanes off of the runway, which is essentially what it is. There are some catapult cables that launch them off and a bit more efficient than a humongous spring. And then we have a 21 meter long runway that this thing goes down. These planes are a couple thousand kilograms and need to have a velocity of 45 meters per second by the end.
So I have no idea how much planes weigh, but I usually think of a car as being a ton, especially the modern sort of SUV cars, and a ton is 1,000 kilograms. So twice the weight of a heavy car. Yeah, I could see that for the big jets. I think that for these tiny little single engine prop jobs that hobbyists have, I would say it's way less than that, but that seems reasonable. 21 meters for a runway for a aircraft carrier. I'm just imagining, they do that sort of tilted runway thing that happens rather than using the full length of the aircraft carrier. That sounds a little short, but especially if I would think the catapult would be more than just the first 5 meters, but I don't really know. And then a velocity of 45 meters per second, what is that, almost 100 miles an hour? Yeah, that seems quite reasonable. Okay, very cool. Let's go.
Into the runway. So I want to know, what would the spring constant be for this launcher? So to be consistent with a lot of the lecture material that you took notes on, we're going to use the energy pie charts.
Cool.
As a way to set up the problem. And so in the initial part of the problem, we have some spring energy and we have some work done by thrust. So I'm going to put WT. So whether it's half and half is not the issue. Hopefully you remember that from the lecture. Just splitting up the pie in as many pieces as there are energy involved in the thing. And then all of that goes into kinetic energy.
Cool.
At the end of which we normally just write with a K, at the end of the runway, or once it's past the spring part of the puzzle here. All right, so the pie charts are just an organizational tool that let you picture in a semi-quantitative way, kind of qualitative a bit too, because we're not trying to be exact with the portions. You'd have to do some computations to know that, and that's not particularly useful in that regard. So how do we measure this? So the capital U is a symbol for potential energy, sub S is a spring, and from the reading and lecturing, we know that the potential energy stored in a spring is 1/2 kx squared, where k is that spring constant. The work done by the thrust is just going to be force times distance. Work is always a force times distance. And then, so that's the initial, that's the goes into part of the problem. Okay? And that's going to...
The Gozinta. That was great. So I was wondering if there was going to be some color coding here, right? So he used different colors to highlight the various aspects of the problem, and I'm still curious to see if ultimately these colors get used when we start to really crunch this stuff. But I wanted to pause and talk a little bit about something. So this thrust, right? So it's really, really interesting to think about how during the first 5 meters, two very different things are happening to this jet. It's trying to get itself going with its thrust, and the spring is doing its thing, right? And so I could imagine students feeling like, well, I mean, this only makes sense if that's the only thing happening, right? Like, how could its energy be increased if it's still connected to a spring that's doing its thing? And so it's fascinating to realize just how much you can sort of set these things separate. And what the pie chart does is really help with that. Like, look, there's some stuff you got to do, and there's some other stuff you got to do, and then it becomes the final. Now, of course, some people do these with bar charts instead of pie charts. And I think what bar charts enable you to do, it feels to me, is to make sure that you can really see the differences and sort of it goes throughout a problem. Pie charts, I feel like, just in general, help you understand relative percentages really well. We're pretty good at judging angles, like, oh, that's bigger than that. Or areas anyway. So I'm not sure if one has a cognitive big change to the other. I think that the notion of the whole pie is really, really cool, although it's interesting that he drew the size of his pies a little bit differently. So it was very cool. Let's keep going.
Equal in the end the kinetic energy. And so the ability to write an energy balance is the main event in these problems. And if you can write an energy balance, then it's a matter of solving for something. You may have to go and find a value or find a way to substitute something away, but it becomes a math problem. So at this point, the physics is technically done. We've done an energy balance, and the rest of this story is going to be a math problem, right? And so just to connect some dots here. So, the first 5 meters, is the spring part of the spring is pushing. So you want to, I'm going to match up the colors.
Oh, cool.
Here with the highlighting. And
very cool.
The 21 meter long runway, well, that's the length over which that thrust force is acting, okay? We have the mass of the plane, and we're going to need a velocity. And I forgot, I left the thrust out. Thrust of...
Ooh, different color. Very cool. So I really like this, right? So the big question is, how much algebra do you do for your students, right? And so what these colors have enabled us to do is, look, we know where the number 2 is on our calculator. We know where the number 1 is on our calculator. The only thing that's not colored here is K. And so to be able to really solve for K, this is doable. But I want to pause for a second and talk about some places where things can go awry, right? So if you subtract this from both sides, you're going to get the kinetic energy minus the thrust that came from the jet engines, right? And there's a possibility that that could go negative. Well, if you look at over here, this is definitely a positive thing. We're not talking about imaginary lengths. This is definitely a positive thing. And so that would lead to a negative K. And so it would be fascinating if you provided numbers. Let's say you were just making up a problem for students quickly, and you provided numbers such that this minus this was negative. Basically, what you'd be saying is that the plane could have done this by itself, right? And that in fact the spring would have had to slow it down. So the K constants are always positive, but it's really a matter of thinking about, are you gaining or losing potential energy? So I think that it's really fascinating to think about numbers. So what I'll do in quizzes for my students, and I'll maybe assign a homework problem like this, and then the next morning, what I do is I assign maybe 4 of them or something, and I'll use a 4-sided die to randomly pick one. And so, someone always groans like, oh, that's the one I didn't know how to do. Or I'll groan like, oh, that was the easy one. But I think that it's fascinating because what I would do then, instead of just having them do the exact same numbers, I would change the numbers around. And what I ended up doing was I would just ask students for random numbers. So, let's see, so there's 5 different numbers here. And so a student would shout out 0.000000001 and a light year, and 1, and 0, and the speed of light, right? And so I'd write all them down. And I'd say, okay, anyone want to say something about the real life scenarios of these? And people say, oh my God, the speed of light, that's impossible. Well, you said that the mass was 0. I think we're going to have some divide by 0 problems, or possibly have some divide by 0 problems. And so sometimes people will say, yep, okay, I think that this is going to be an extraordinarily unreasonable result, so let's go. And then other students would say, oh my God, please, can we just use some numbers that are more realistic? And I'll let them change, which one is bothering you the most? And often in that example that I just gave, it would usually be the 0 kilograms of the plane. And so it's fascinating to think about whenever you set problems up like this. If you're going to have a subtraction, well, what happens if it goes negative? So I think that's really interesting. This is great. I'm just going to stop here. The color coding was great. I think that the way that he was sort of using these pie charts and reminding students the value of them was really good, really cool. All right, everybody. Well, hey, have a great day. And remember, physics teachers are awesome.